Did you know that South Africa technically has two different rainy seasons? In winter, the Western Cape gets most of its rainfall, but in summer, the rest of South Africa gets its rain. So we've already looked at the mid-latitude cyclones that bring rain in for the Western Cape, but today I want to take a look at the anticyclones and the thunderstorms that bring the rain for the rest of South Africa. I will admit that anticyclones did seem to cover a few more topics that aren't included in this video, like berg winds and cutoff lows. But in this one, I wanted to focus on the anticyclones themselves and the thunderstorms that they bring. So specifically the line thunderstorms. So let's check it out. Of course, I would just like to add that this may be a frequent way of asking these questions. It doesn't mean that this is the only way that this topic can be examined. There's no guarantee on what type of questions will appear in an exam paper or even if it will be in a paper. Okay, so let's start with anticyclones. And it seems to be a bit of a pattern for all of these atmospheric science questions, but they all start with identify the feature. So they just love to give this. I think at this point we just need to expect these types of questions in the exam. So they'll give you a labeled feature. In this case over there, we have C. Don't mistake it for the H. The label is the C. And over here it is E. Okay, in this case, they want you to name the anticyclone or the high pressure cell. So I don't know if you can really make it out from this image over there, but here is South Africa, right? And there it is. So you have to take a look at which side of South Africa the anticyclone is on. And over here we can see it's on the western side. So this is the South Atlantic high pressure. Okay, do include the South in the name. They would also accept the South Atlantic anticyclone. That's also fine. Okay, so if it's on the western side, then it's the South Atlantic high pressure. Here we can see it on the other side, on the eastern coast, or the eastern side. There is label A, there is label D, and there is label B. Okay, those ones are labeled or are indicating the South Indian high pressure. They also accept the South Indian anticyclone. Then one that we see depending on the seasons, and we will explore that a little bit more, is the Kalahari high pressure or the Kalahari anticyclone. So this is located over the interior. So it's located over the land in South Africa, and it's basically caused just by the air being very cold, that the air sinks and it forms this high pressure. But we will take a look at this formation. Okay, so if it's labeled like over there, we've got G. There we have P pointing towards the high pressure. We have B. You can't really see the label for the high pressure over there, but it is there. And we have G. Then we know it is the Kalahari high pressure. Okay, sometimes they will ask you to identify a trough or a ridge. Now, this is different to just a low pressure and a high pressure. A trough and a ridge is an elongated section. So if you see this line, you see over there we have a low pressure and over there another one. And you can see they actually have this dotted line connecting the two. Hopefully you can make that out. Here you can see it as well. There's the low and the other end. Okay, I see I kind of cut it off. There's the other low. But again, they have this line, this long arrow connecting the two. And there and there. Okay. If you have this long stretch of low pressure, they'll indicate it with this long section of the line or the label. That is a trough. And then the same for the other way around. Here again, we have a high. It's labeled with this long arrow there. Or here with just this line, they've labeled B. That is a ridge. Okay, so in this case, they're not asking what this high pressure is called. They're asking what this elongated section of high pressure is called, and that's a ridge. So that's the first thing I want you guys to just keep your eyes out for, because I feel like a few people might get slightly confused by what exactly they're looking for. Then, the thing to know about the anticyclones is that they are very much influenced by the seasons. So, how they move and where they are located and how strong they are is completely dependent on the season, and it does influence the type of weather that they bring. So, most of these questions you're going to see are split between summer and winter. And that is how we can also identify the season on a synoptic weather map. Now, we already looked at the winter synoptic weather maps when we looked at mid-latitude cyclones, because then the go-to piece of evidence is look for the cold front. When it is summer, look for the low pressure over the land. Okay, that is usually the clue that it's summer. You would also find the high pressure over here, right? That is further south. Okay, so here we can see it again. The low pressure inland, there and there, and the anticyclones are further south. The other thing that you can look for, we can't necessarily see it on this one, but we can see it on this one, is the temperature. So you can just take a look at the temperature and see, does it look warm? Does it look cold? Summer, winter. They won't always just ask you to identify the season. Sometimes they will tell you the season and say, give evidence to confirm that this is summer. Then you look at what you can see. If you can see that there's warm temperatures, then say warm temperatures. After that, look for the low pressure over the interior. Okay, that's your first piece of evidence. Then you take a look at where the high pressure is. If it's further south, so around 40 degrees south, also implies summer. Clouds, we're going to see now where we get summer rain. So clouds, thunderstorms, all of those things, summer rain, it's summer. And you might not see a mid-latitude cyclone, but if you do, it would be further south. In this case, there we actually do see the cold front. We can see it's further south. It can't quite reach South Africa. In this one, it wasn't even included. And there again, you see a little corner of a cold front. Again, it's further south. So this is mostly just to recap what we did with the mid-latitude cyclones previously. But when we have winter, you will see the cold front reaches South Africa. But a big clue is the high pressure over the interior. Okay, so we see a high pressure there, a high pressure there. And hopefully you already know the name. That is the Kalahari high pressure, or the Kalahari anticyclone. So once again, they might not just ask you what season it is, they might ask you for evidence. So in winter, we have high pressure over the land. We can clearly see, well, hopefully we can see that it's cold. Sometimes they don't give the temperatures, then you can't assume that. So we can see that it's cold. We might be able to see that there's clear conditions, that there's no clouds. We might even have some type of evidence or report of frost. Then you can also assume that it is winter. The land is dry because we get summer rain, not winter rain. Well, you know, the rest of South Africa, not the Western Cape, they do their own thing. And we would see a cold front reaching the Western Cape. Now we're explaining why we have this low pressure in summer. So you might see a map like this where they'll give you this low pressure over the interior or over the land, and they ask you, why does that low pressure exist? The short answer is because it's warm and warm air rises. So the full explanation is because it's summer, we have this warming process, we have this warm air, the warm air rises, and because it rises, it's lifting the air off of the ground, and we have less pressure on the ground, hence low pressure. Now we look at the opposite. Why do we have high pressure over the interior in winter? Again, now it's cold. Cold air is more denser, it subsides, and as it subsides, it sinks and applies pressure to the surface of the earth or to the ground, and then we have high pressure conditions. Now we get to the more exciting stuff. How do the thunderstorms form. In summer, we see these occurrences of line thunderstorms. So over the interior, we get this stretch of thunderstorms that occur because of the low pressure over the interior and the anticyclones on either side of the coastline. So in this case, I've abbreviated it, but we have the South Atlantic high pressure and the South Indian high pressure. Okay, so I've abbreviated it, but in your exams, give the full name. Okay, so the wind moves away from the high pressure, the South Atlantic high and the South Indian high, and they converge and move in towards the low pressure over the interior. The South Atlantic high pressure brings very cool, very dry air from the southwest. The South Indian high pressure brings warm, very moist air from the northeast. Okay, where they converge or where they're drawn in at the low pressure, we get what we call a moisture front. Hopefully you remember what a front is. So a front is a point where you have two very different air masses meet. And in this case, they're different in their moisture content. One is very moist, one is very dry. That's why we call it a moisture front. Then the warm, moist air is forced to rise over the front, and that sudden rising causes condensation, thunderstorms, and just extensive rain. And this rain is most clearly felt on the eastern side of the front. Now, they might not just ask you to explain it, they will most likely ask you to draw a diagram that shows this process. There are several different ways that you can draw this diagram. Check to make sure that the question isn't clarifying what type of diagram they want. So in this one, I'm doing a top view diagram. In this particular case, they actually gave the outline of South Africa, and they said using the diagram that they gave, the outline, explain how the line thunderstorms form. So they wanted a top view. We have the South Indian high pressure, South Atlantic high pressure. You see the wind or the air moving away from the anticyclones, away from the high pressure, and towards the low pressure over the land. Where we have this low pressure and we have these two types of air mass meet, we have a moisture front. Make sure you've labeled the characteristics of the air. So noting that this is cool and dry, noting that this is warm and moist, and actually labeling that this is the moisture front. Then this is where we'll have the thunderstorms, typically more on the eastern side, and that is where all the rain comes from. So there's just a couple more diagrams to show the same process. All of these are from memos from exam papers, so that you can see it's very much the same process that they're looking for. We have, again, South Indian high pressure, South Atlantic high pressure, warm, moist air. Again, they're looking for the characteristics of the air, cool, dry air. And in this case, they also identify the direction. So northeast versus southwest, okay, in case it's not clear in your diagram. There we have the line thunderstorms, we have the moisture front that's being shown, we have the low pressure over the interior, and we'll get the thunderstorms. Okay, now it's same thing. Moisture front, wind blowing in from the high pressure, blowing towards the low pressure, converging, thunderstorms. They might just ask you to draw a cross section. If they ask for a cross section, it will look something more like this. Now, in this particular case, they gave this part of the cross section. So they gave what was supposed to be the cross section of the topography of South Africa. So that is supposed to be the eastern coast. This is supposed to be the western coast, and South Africa, we hopefully know, is kind of like on a plateau. We have the escarpment over here and here. So we had to draw, again, the warm, moist air coming from the South Indian high pressure blowing over there. The cool, dry air from the South Atlantic high pressure blowing in there. Where they meet, we have a moisture front, got the warm air rising, and it forms the thunderstorms. Like I say, very similar diagram. This again was from a different exam paper. This time they didn't want the whole details of the topography. They just wanted you to show how the moisture front was formed and how the thunderstorms form as a result of that. Next question. Why do we see line thunderstorms in summer? For starters, the high pressure cells shift southwards. Okay, so as summer comes around, we have heating further towards the south. So the pressure cells, most of the systems, they all shift further south. And with that, we tend to also see blocking of the mid-latitude cyclones, so the Western Cape doesn't get as cold fronts anymore. Okay, with the high temperatures of summer, we see hot air rising and low pressure forming. This low pressure actually has a name. It's called a thermal low. So basically, as the hot air rises and we have that low pressure, that whole system is condensed into a thermal low. Then the warm, moist air blows from the South Indian high pressure towards that interior low pressure, and that is why we have the thunderstorms. What kind of weather can we expect with these thunderstorms? Well, rain, lots and lots of rain. Of course, lightning, thunder, and just incredibly strong winds, like tornado, gale force type winds. And in exceptionally strong storms, we would also see hail. But despite the excessive rain and hail and tornado-like winds, these thunderstorms are very important for South Africa, for the interior regions of South Africa. Why? Well, because we need the water. Okay, that is the main source of water. We use it for our agriculture, our industries, domestic use, all of the above. So if you can think of any area where you would need water, these thunderstorms, that is their main, if not only, water supply. Now, in this question, they just wanted to make sure that you understand the difference between a line thunderstorm and just a regular isolated thunderstorm. Well, the line thunderstorms, because you have so many, they tend to be a lot stronger. You have this collection of cells, this collection of thunderstorms all happening at the same time. They tend to last much longer. They cover a much bigger area. They are just continuously fed and fueled by the moisture coming in from the South Indian high pressure. So we just have this constant strong uplifting of air, constant supply of moisture and fuel, so it can just keep on going for days. Also, it can happen any time of the day, unlike your isolated thunderstorms that happen only at certain times. Now, your isolated thunderstorms, for one, it's just one thunderstorm. It's not a whole team of them, but they also don't last as long. So they have much shorter durations. They cover a smaller area. They don't have that constant supply of moisture and fuel to keep them going. And they usually only occur in the late afternoon when temperatures start to drop. So in this case, it's the change in temperature that causes the thunderstorms. And in this case, it's the moisture front that drives it. Okay, what can people do to prepare for these thunderstorms? For one, they can just try to stay indoors. So they can try to stay indoors, wear out the storm, maybe avoid any type of low-lying areas, move to high-lying areas where possible, especially if there's a chance for floods. So avoid areas that are near rivers. It's very easy for those places to get flooded with that extensive rain. And just listen to any type of updates or warnings that might come from the news or other sources of information. Now, this is one that seems to pop into quite a few papers, and that is the Cape Doctor. The Cape Doctor is also referred to as the Cape Southeaster. How does it form? It blows over, in case you couldn't tell by the name, it blows over the Cape. So not just like the whole of the Western Cape, but very specifically around here. The Cape Doctor or the Cape Southeaster is a wind that occurs in summer when we have this high pressure off of the Cape. The high pressure moves in a anticyclonic direction. So that means that the wind blows from the southeast and it blows over the Cape. So I have seen them ask a couple of times to draw diagrams to just explain how the Cape Doctor or the Cape Southeaster forms. And this is basically all they're looking for. They're just looking to make sure that you've got the South Atlantic high pressure over here, and then the wind blowing in an anti-clockwise direction that blows southeasterly over the Cape. It's referred to, I believe, I think, as the Cape Doctor because it blows a lot of the pollution away from Cape Town. Why is the interior dry, stable, and clear in winter? Now you're going to notice that we've switched seasons. All of the questions up until now have been summer based. Now we're going to look at how the anticyclones influence winter months. And for one, we have very dry and clear conditions in winter. As the air gets cold, it contracts and subsides. That sinking air puts pressure on the ground, and we have the formation of the Kalahari high pressure. As the air sinks, it is heated adiabatically, which means that it's just heated because it's placed under pressure. And with this heating, we have the formation of an inversion layer. So that means we have a layer of air that is warm. And with that, with this inversion layer, we actually have stable conditions. So we have cold air on the ground, and then we have a warm layer of air, and that's considered quite stable. And it means that wind and atmospheric stuff can't really move around in that conditions. It also means that we can't have any cloud formation. The air can't rise for condensation to happen. Inversion layer blocks moist air movement over the escarpment. So if you remember, the moisture comes from the South Indian high pressure. But if we have this inversion layer, this blocks the wind. So we can't have this warm, moist air blowing into the land because it's blocking it. So it's kind of like halfway down the escarpment, which means that any wind trying to blow towards the interior can't make it all the way over the mountain or over the escarpment. Explain how the presence of an anticyclone can make smog or air pollution worse. So I have seen it referred to as smog, but if you're not familiar, this is also just referred to as air pollution. So how can the anticyclone make air pollution worse? Well, it relates back to that inversion layer that we were just talking about. So the high pressure means that we have the sinking air. The sinking air applies pressure to the air. It causes heating, adiabatic heating, and we have an inversion layer. Again, I said so this creates a stable atmospheric condition. We have cold air on the ground, warm air higher up that is stable, which means that we don't really have movement within the atmosphere. We don't have any type of wind to blow it away, and the pollution becomes stuck there. We have the sinking air puts pressure over the land over here that creates a inversion layer with the adiabatic heating, and all of the air underneath is trapped. Okay, all the pollutants, everything, it can't go anywhere. You might see something like this very early in the mornings in winter, maybe when you're driving through a landscape or farmland somewhere. You might see in the distance a bit of smoke or something else that rises up, and it almost looks like it hits this glass ceiling and it can't float up any further than that. That would be an example of the inversion layer. So the same way the smoke can't rise any higher than that layer, the pollution can't get through that. And then finally, I think this is the last question. Why does the inversion layer change with the seasons? So it actually changes its position depending on if it's summer or winter. Well, in winter, cold air sinks, which means that the inversion layer is closer to the ground and everything is kind of trapped below that, and it's very often below the escarpment. In summer, warm air rises, so all of the systems rise with it. and that includes the inversion layer. It's halfway down the escarpment, so it's blocking the wind from reaching the interior. But in summer, this would rise, and there is a clear gap for the wind to be able to blow over the escarpment, under the inversion layer, and towards the low pressure in the interior. I know this is probably a lot of information dumped on you, but hopefully you're starting to see the pattern with the summer versus winter, the Kalahari high versus the low pressure, and the difference in the conditions that either result in the line thunderstorms or prevent it. So thank you very much for joining me again for this video. I really appreciate the time. And of course, I do just need to give credit to SlidesGo, which is where I found the template for these slides. It's very nice to not have to make up all of these designs myself, but just focus on the questions and the answers that we're here for. Thank you so much for taking the time to go through all of these questions with me. I hope that you have found this really useful, and good luck as you guys prepare for your final matric exams. If there are any other questions or topics that you would like me to go over, let me know and I'll see where I can help. Okay, thank you. Cheers. Bye.